us start our discussion with the quantum algorithms. Okay? So, quantum algorithms. First of all, we have to motivate the quantum algorithms. Right? We have to motivate why we're learning about quantum algorithms for the first time. So, first of all, quantum algorithms will give us, different way of observing problems. Okay? So this is going to be the first reason that the interpretation of classical questions, interpretation of classical questions or problems with a new look. So that's a different perspective. That's the first thing. So we can actually generate from classical problems quantum problems. Okay? That's the new look we're talking about. Quantum problems. And of course, the speed up, right? That's why we're having all this hype in the media. Speed up. Some of the, not all of them, some of the known problems, or hard problems, let's say. Okay? Hard problems. Some of the hard problems. Not all of them, but some of them. Because we know, for some of the problems, that classical computers excel. They're kind of, from a master point of view, there are very, very well-known classical questions, and there are very, very well-known classical algorithms, and that can solve these hard problems very efficiently. That's why I'm saying, a subset of these hard problems are very, very to our concern, very important questions, and we expect some speed up, from quantum algorithms. Okay, so so these are two important motivations for quantum algorithms. But in order to talk about or start understanding why we're learning about quantum algorithms, is that we need to first understand the complexity classes. Okay, so let me just talk about complexity classes. What are those? Polynomial time algorithms and non-deterministic polynomial time algorithms. Have you ever heard of them before in your previous classes? Like algorithm analysis class, for instance. They may actually, no? Or maybe there's a complexity theory class which you haven't taken, probably, so far. But anyway, this is just a small, very easy introduction to that class of subjects, different subjects. Okay, so I'm going to start with in order to discuss this, I'm going to give you an example, okay? Just to, illustrate what we're discussing. So first of all, I'm going to ask you 4 different questions. A, B, C, and D. A is, find 2 whole numbers. Okay? Then, of course, those whole numbers are not 1, okay? But those whole numbers such that whose product is, let's say, 35. Can you tell me? 2 whole numbers whose product is 35, other than 1? Tell me 2 integers, please. 7 and 5. Correct. 5 and 7. Right? Okay. Let me just ask you another question. Find 2 whole numbers whose product is 187. Can you tell me that? It's a bit harder, I assume.
18.7 product test.
Yeah, but we're talking about integers only, so whole numbers. So let me just tell you the answer. 11 and 17. Okay, 11 and 17. That creates 187. And let me ask you, continue. So this is 2-digit, right? 2-digit. This is 3-digit. So I'm actually continuing this way. 4-digit, 5-digit. Okay. So find whole numbers whose product is 2407. Okay? Let me give you the answer. It is 29 and 83. All right. And final question. Find 2 whole numbers whose product is 88,631. Can you tell me that? Tolga, you have a guess? No, of course. Well, you could if you have given the time, right? Probably that's right. Okay, so let me just give you this answer. 337, or 337, and 263. All right. So as we go along this way, you're actually seeing that finding these two whole numbers is becoming harder and harder, right? Harder and harder. Okay, so complexity increases, apparently, right? Complexity increases. Okay, so let me give you another set of questions. Okay, this is one set. This is one set. First set, let's say. Okay, so now second set. In the second set, I'm going to actually ask you questions, again, related to this. Okay, but I want you to assess the complexity. So, first question is, multiply 7 and 5, okay, and verify, or check, it is equal to 35. Okay, so I want you to do this multiplication and check if it is equal to 35. Okay, this is for 2-digit. Second, so this is a, let's say, bar. This is a bar. This is related to this A, that's why I use a bar. Let's say B bar, multiply 11 and 17 and check or verify that it is equal to 187. C bar, multiply 29 and 83 and check, verify that it's equal to 2,407. And finally, D bar, multiply 337 and 263 and verify check is equal to 88,631. All right. Now let's just focus on in this set. Is the complexity increasing as we go to 2-digit, 3-digit, 4-digit?
Yes.
Yes, increases. Complexity increases. Let's compare now increasing here, complexity, and increasing here. Which one is increasing faster? I'm thinking about, so if I given you this, Tolga, 337 and 263, how much of your time would it take to figure out whether it's going to be equal to 88,631 or not? Couple of minutes maybe. How about this question? Find two whole numbers whose product is this, without knowing these two. How much of your time would it take to figure out these two numbers? Maybe half an hour, right? So apparently, the increasing complexity here is probably higher than complexity increasing here. Verification is an easier process than finding the actual two whole numbers, okay? So therefore, we have to quantify this. In other words, both directions here, complexity increases. However, we believe, we sense that the time it takes to compute the solution, this is higher than this, okay? But this is not apparent from this discussion. Both of them are increasing, but which one is increasing more than the rest, right? That we need to quantify. That's why we need complexity analysis, okay? So, let me just define a bit more formal way, okay, so in my discussion, in order to quantify things, I need to define some terms. For example, Tn. This is just like the algorithm analysis you learned, right? This is the time or number of steps. Let's say number of steps to solve a question or a problem, okay? Or a problem. All right? Of length n. So I have to define n. Length n. It's like you can think of this as an input, for example. Input of length n. And it goes to a function. And then it increases, of course. So I'm going to define the following. If this Tn is smaller than or equal to k and p for two constants k and p, then I call this polynomial time, because this is a polynomial, okay? Polynomial time. Of course, we have to make sure that n goes to infinity. This is still satisfying for k and p constants. Okay? So Tn, even if n goes to infinity, Tn must be smaller than or equal to Kn raised to the power p. What are those Kp's? You select them appropriately, such that this is true. But these are constants, they're not function of n. Okay? So this is the polynomial time. We usually actually use p, bold p, to represent polynomial time. Okay? If on the other hand, Tn is greater, strictly greater than k c to the power n for two constants, again, constants, k and c, for, of course, n goes to infinity, okay, then we call it exponential time. Why exponential time? Because this is an exponentiation. Right? C is a constant, c to the n. As you can see, this is a bigger number compared to a polynomial. Right? So this is now we're defining exponential time. Okay, so this is usually tractable from computer science perspective, since you're computer engineers. So you really gotta know this. This is tractable. I mean, treated as tractable. Tractable problem. Okay, this is non-tractable. Okay. It's really hard to track because it's just got out of hand because of complexity, right? Okay, so this B4, this test, okay, is called polynomial time. This is polynomial time for short. Okay, this is P class. How about this class? This is harder, right? We know that this is harder. Okay, is this exponential time? Finding the roots so that you get that. Is it exponential time? We don't know that. Okay, we don't know that. I mean, no one has proven that this is exponential time. But this is higher, right? Complexity, in terms of complexity, this is polynomial time because it's just a multiplication of two numbers. Okay, this is known to be polynomial time. However, this is not known whether it's an exponential time or a polynomial time. It is higher than this. Higher than this, I mean, as a sense of computation, because it takes time, more time to compute it. Okay, but we don't know really. But maybe it's somewhere close to polynomial, somewhere exponential. We don't know. Okay, but that's why we define something else, which is called non-deterministic polynomial time. Okay, because exponential time is kind of, an extreme point. I mean, if your problem is exponential time, you don't have a luck to solve this problem. It's just gone out of hand. When n goes to large numbers, you cannot solve this problem. It's just too complex. Okay? So you are given a problem. Okay? Let's just assume that you are given a problem and a solution. If checking the problem solution is polynomial time, then the problem itself is non-deterministic polynomial time. That's just a definition. Okay, it's kind of a theorem, by the way. So therefore, this set is NP problem. This is just a definition. Okay, we define non-deterministic polynomial time because we believe, as a computer scientists, we believe that non-deterministic polynomial time is a harder set of problems, comprise harder set of problems compared to polynomial time. That's why we define it, because it's appropriate to define it that way. Non-deterministic polynomial time is believed to be, okay, it's not proven, by the way, it's believed to be more complex than polynomial time, okay? But exponential time is proven to be more complex than polynomial time, okay? So this non-deterministic polynomial is somewhere in between, okay? We don't know whether it's equal to this or somewhere actually in between. We don't really know that, okay? But there is a certain sense from computational point of view that this is probably bigger or more complex than polynomial time. So we know that, we know the following, okay? We know that let, for example, x be a problem, okay? And x is in P, polynomial time, okay? And we also know that P is a subset of NP. Okay, this polynomial time is the solution. Checking the solution is easy. That problem must be harder or equal. Okay? Otherwise, that would not make sense. It's just the definition of NP. All right? So we know that is the case. How about the following? We don't know the following answer. Is this a correct statement? NP is smaller than or equal to, or maybe a subset, or equal to this P. We don't know this answer. Because if that's the case, then we know from these two, NP is equal P. This is a Millennium Prize question. If you're able to solve this, in other words, if you're able to show this, then you got a $1 million prize. Okay? Computer scientists couldn't prove the NP to be a subset of P. Because most of the computer scientists believe, we couldn't do it mathematically, by the way, but most of the computer scientists believe that there is a set that is NP, non-deterministic polynomial time, and P is only a subset of this. So there is some space between them, okay, that are harder than the problems in this set. Okay, for example, this problem is this one, they believe, this one. Okay, finding true whole numbers that would give you a big number. This big number, I mean like 400-digit number. It's not just 5 digits. Okay? And this, they believe that this here, let me just call it X. So X, problem X here, okay, is believed to be harder than the solution to check, which actually probably lives in here, is polynomial time. Okay, and the problem itself is something that is not in polynomial time. Okay, that's what they believe, because they believe that it is a harder problem. And as you can see, it's a harder problem. Okay? I mean, it takes more time at least. Okay? So, why is this so important? I mean, this specific example, why this problem is very important? Because there is an cryptographic function or cryptographic algorithm called RSA that lies the whole security of internet today. Okay, and RSA is based on the solution of this problem. If you're able to factor this number, this big number, about 400 digits, for example, into two whole numbers, actually these are primes. Let's assume that these two are primes. If you can factor this big number into two primes, then you're able to crack any message you like in the internet. And that's why it's important to consider this particular problem. Why the RSA is based on this particular problem? Because we believe that factoring a big 400-digit number into two primes is a hard problem. Okay, NP hard. Okay? That's why people base their cryptography, procedures or routines onto this particular problem, dividing this or factoring this number into two primes. Okay, so there is no known polynomial time algorithm to solve this problem. Okay, as I said before, polynomial time algorithms are tractable. Okay, but there is no known. That doesn't really mean there is no algorithm. Maybe there is one we couldn't figure out, but there is no known algorithm, polynomial time algorithm that is tractable to solve this question. That's why people base their cryptographic routines on this specific problem. However, there's a quantum algorithm that solves this problem in polynomial time. Okay? For example, Shor's algorithm. Okay? Which we were going to talk about later on in our next class or so. Okay? So, would that motivate you guys? Is this motivational? Because we're solving a problem that is not polynomial time in classical computation, but it is polynomial time, and there's a specific algorithm that's polynomial time in quantum realm. Okay? That basically explains why we are dealing with quantum computation as one of the good reasons. Okay? All right. So let me also talk about, so I actually defined complexity in terms of number of steps that an algorithm takes to compute the solution of a specific problem. However, there are other complexity definitions. One of them is the query complexity, and I'm going to now touch upon the query complexity a little bit, because the first algorithm I'd like to cover today, which is Deutsch algorithm, is based on query complexity. Query complexity is defined as follows. So we have a specific functionality, okay? And you would like to know what that function is doing. So you need to first provide an input and get the output. So based on that input-output relationship, you figure out what the function is doing. So that is one query. And if you need to ask another question to learn more about the function, that is your second query, okay? So the query complexity is the number of questions you're asking to the function that's going to tell you the output, so you can figure out what the function is doing, okay? That's the definition of query complexity. So we'll actually learn three different classes of algorithms. One is the Shor algorithm that factors a big number into two primes, for example. That's the first class of algorithms. The second class of algorithms is based on evaluating functions and the query complexity. There's a function and you would like to evaluate that function multiple times. That's going to give you the query complexity of your algorithm. And finally, there are also algorithms to ease search, okay, that we will go through, the Groover search algorithm, that's going to decrease the complexity of search. Because we know, as you may know from your algorithms classes, right, the search usually takes linear time. I mean, the best search algorithms takes linear time. I mean, there is no search algorithm that is lower or sublinear. But there is a quantum algorithm with Groovers, it's sublinear in n, the input length, okay? That's also an interesting algorithm that's going to constitute the third class of quantum algorithms. Okay, so we're concerned primarily with the evaluation of functions. Deutsch algorithm, Deutsch algorithm, and Simon's algorithm will cover. So here's the definition of these. We are given n number of functions. N number of functions, okay? And n number of classes. Okay? And n is, of course, greater than or equal to n. Right? So those functions could be classified with one of those classes. Okay? So you can, let me give you an example. There may be 4 functions, for example, and 2 classes, okay? And you would like to know, by just evaluating the function, which class it belongs to. Okay? That's, for example, is, this could be also used. Okay. So we're given n number of functions and n number of classes, and n is greater than or equal to m, and we would like to classify those functions. And the first attempt to this question was given by Deutsch. Okay, and this is a German guy who came up with this first algorithm. Okay, Deutsch algorithm that is proven that at least in theory there's a quantum algorithm does better than a classical approach. The problem is quite simple in the problem of this Deutsch algorithm that we would apply to. However, from historical perspective, this has got a certain meaning. In other words, this algorithm solves a specific problem by using smaller number of queries, okay, compared to classical approach. So let's just consider the following. All 1-bit inputs, functions, and all 1-bit input and all 1-bit output. Or maybe let me just use single all because it's going to be complicated. So let's just say all 1-bit input, 1-bit output. Okay? Functions. How many of them do you think? All 1-bit, 1-bit output, 1-bit input functions. How many of them do you think we have? We learned that in EE 203, if you recall. This was the formula that we use. N is the number of bits. N is 1, then you got 2 to the 2, which is 4 different functions, right? It's just considering all 1-bit input and 1-bit output functions. So let me tell you what they are. There are 4 of them. What they are. So let me just name those functions f0, f1, f2, f3. So f0, 0 equals 0, let's say, and f0, 1 also is 0. This is constant zero function, okay? So I'm going to just call it constant zero function, okay? This is one of them. Let's just write the second one. Let's just assume that f1, this is the other function, f1, 0 is 0, and f1, 1 is 1. This is identity, right? Whatever the input is, you see at the output. So that is identity. Identity function. Okay? Now we got f2, and f2 is 0 equals 1, and f2, 1 equals 0, let's say. That is inversion, right? Inverter. Just like inverter gate. Okay? And that's identity gate. This is constant 0 gate, and there's a constant 1 gate. Okay? These are all possible functions you can generate for one input, one out, one bit input, one bit output. So this is called inverter function. Okay, and f3 0 equals 1, and f3 1 equals 1. That is the constant 1. Could you please help that to get into the class? Okay. So we have this constant 0, identity, inverter function, and constant 1 function. So therefore, one of the things we realize about these functions is that we can define two classes for them. One class is the constant class. Okay, this is constant class. And the other class, so I assume two classes. The other class is a balanced class. Why? Because output is half of the output is 0, half of the output is 1. There are two actually in this case. The half of them is 0, half of them 1. In other words, 1, 0, 1, 1. Here is also 1, 0, and 1, 1. So that I'm going to call balanced class. Why did I say, why did I actually define these terms in more general? Because outputs could be, inputs actually, number of inputs here is just 1. But a number of inputs could be 2, 3, 4, 5. So therefore, the outputs could be balanced. In other words, if you got 2 inputs, for instance, then you have how many classes? 2 to the 4 is 16, right? So 16, meaning that you have 2 constant classes, like 0 and 1, and then the rest may be balanced, may not be balanced, right? So that's why I'm trying to make this problem general. And there's a generalization to that, by the way, called the Joseph's algorithm, which I will cover later on. But here, this 2 is a balanced class, and this 2 is a constant class. Okay, so from classical perspective, let's just walk through the classical problem first, classical solution, first, and then we'll talk about the quantum approach. In the classical approach, you are given this, a black box, let's say, F, and you are asked questions, okay? And this function will tell you an answer. For example, you can ask me, what is your output if I send you 0? Okay? And I pick a function, and you guys ask me this question. What is the output? I'm going to say 1. Can you determine the function? Can you tell me what function I am assuming? Is it f0, f1, f2, f3? The question is, how many questions should you ask so that you make certain you figure out which function I choose? Because I choose a function and I don't tell you which function I choose. Can you tell me? For example, if input is 0, let's say I said output is 1. Let's look at it. Okay? Are there one function with this input-output combination or multiple functions? Okay? So there are 2 functions. Which are them?
F2 and F3.
F2 and F3. So you cannot determine which one I pick. Right? Then you have to ask another question, right? So you would say, oh, okay, what's your output for this input? Then I'm going to say, let's say 0. Then you can determine which function you're talking about, right? Which one is F2, right? Because F2 0, 1 and 1, 0, right? So that you need at least 2 questions to ask and determine which function I picked. Okay? You can actually go through with another example if you like. I don't know if you're convinced, but if you're not convinced, maybe we can walk through another example. Let's suppose that you said, what's your input, output to the input 0? Then I say 0, let's say. Then there are two options, right? Because F0 is 0, and F00 is 0, and F10 is also 0. So you need another question, which is, what is your output to the input 1? Then I have to tell you 0 or 1, and from which you can determine whether I picked F0 or F1. Okay? So therefore, the classical approach requires two questions, two queries, okay, to be able to determine which function I choose.
30 minutes plus. 30 minutes plus.
But I actually opened it up later on, so I've got 21 minutes. That's fine. Okay, now, so this is determining function, but what I want is the class of the function. Not the function itself, but the class. So the question is, can you determine? Because if you determine the function, you can determine the class. Okay? For example, if you determine it's F0, then you can say it's a constant class. If you determine that it is F1, then it's a balanced class. If you determine that if it's F2, then it's an inversion function, which is balanced class. Or you determine F3. So you need at least two questions to figure out the function. That's fine. But how many questions you need to determine the class? Maybe it's easier. Okay? But unfortunately, as I just walked through it, you need, again, two questions to determine the class, to determine which class it belongs to. For instance, as I said before, in the previous example, you figure out if it's either F2 or F3, right? When I said the F0, when you have an input 0, output is 1, when I said that, you would probably say, oh, it's either F2 or F3. But unfortunately, they belong to the different classes. So you cannot determine the class, whether it's balanced class or a constant class, okay? Or if you say, what is the input output when I input 0, then I said it's 0. That's not 1, but it's just 0 in the second example. And in that case, unfortunately, you cannot determine the class either, because it's either balanced or a constant. Because one of them belongs to balanced, the other belongs to the constant class. So you cannot determine that. That's why you need extra question to resolve, which class it belongs to. Okay? That's why so therefore, in classical approach, you need two queries. Okay? Not just determining the function itself, but also determining the class itself. Okay? But as you know, there are two classes. 4 functions and 2 classes. It's just unfortunate that the classical approach couldn't resolve the class determination, because class determination is an easier problem compared to the function identification. Okay? You see, the function identification is a harder problem. There are 4 possibilities. But class identifications may be easier because there are only 2 classes. And quantum's Deutsch algorithm, this quantum version, Deutsch algorithm, actually requires only single query, single question to determine which class the function belongs to. And I'm going to now go through that. Okay? How is it possible for quantum version, the Deutsch algorithm, to figure out this problem in a one single query? Okay? That's our next goal now. Okay, in order to do this, of course, I need to draw a gate which will have f function implemented inside, but we don't know, it's just like a black box. And I'm going to now put that gate into my circuit so that I can only use that gate only once, so that that's a one single query, and I'm going to tell you the result, whether it's a balanced class or a constant class. So I'm going to first define my gate. Okay, that's my gate. It has to be reversible, as you know, because it's a quantum circuit. This is X and Y. I have got 2 inputs, and this is actually as is. The output just goes through as is. And the other output is Y XOR Fix. This Fix is actually one of these functions. F0, F1, F2, or F3. Okay? We don't know which one, because somebody has picked it. He doesn't tell us which one of these functions has picked. And then I'm going to just say Fi. Okay, one of those functions. But we don't know what is inside. We're going to use this gate. But then before we use it, let me just go through the the truth table. Okay? In other words, let's just go through what these x and y's are. And this is output, of course, right? Cat x. And this one, y XOR f(x). So this is 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 1, 1. And what is this? This is going to be 0, 0. So XOR with a 0 is going to give it, the function itself, by x, right? But since x is 0, so I'm going to just put a 0 here, right? 0, okay? And what is this? Y is 1, right? So this is 1 XOR fi 0 because x is 0. I'm just replacing it, okay? That's what I'm doing. This is fi 1, and this is fi 1 plus or XOR 1, okay? Is it 1? Yes, it's 1. Because y is 1, okay? Okay, so for instance, if the guy, whoever, picking this function, chosen I to be 0, then this is going to be f0, 0, okay, which is, you know what f0, 0 is, right? 0. So this is going to be 0. If, of course, I is 0, okay, and then you got f0, 0 is 0 plus 1, you got 1, or XOR 1, 1. This is f0, 1, but this is also 0, okay, and this is f0, 1, 0, and this is 1, right? You can actually figure out the output based on the input and the function, input and the function, okay? Okay, so this is the gate, okay? We don't know which function is chosen, but we're just going to put it in our circuit and see what happens. Okay, so here is my circuit. This is the Deutsch algorithm, actually. Okay, it's just a quantum circuit, okay? So here is how the guy did. He sent the 0 to an Hadamard gate, and a 1 also in a Hadamard gate. And the output of these Hadamards get into this gate that we produced based on the function selection, fi. We don't know which one, okay? And then the output goes to another Hadamard gate, and then we have a measurement, okay? We don't use this output at all. And the measurement result will tell us whether this is a balanced class or a constant class, okay? And we'll see how that works, okay? Not sure if I'm doing right something, but anyway. So these are constant, these are balanced. Okay, so apparently, you see these are kind of classic bits, right? And then we prepare the states, 0 and 1, and then we walk through this Hadamard gate transformation because we want to put them into superposition so we can actually explore a bigger possibility, space of possibilities. And then it goes through that fi only once, just once, we use that once. And then gone through the first qubit, goes through another Hadamard gate and a measurement, okay? And the measurement will tell us whether it's a constant function or a balanced function. Okay, so let me first talk about these Hadamards, right? Because there are two Hadamards here. And we remember if the Hadamard gate transformation matrix, 1 over square root 2 of 2, 1, 1, 1 minus 1, right? And if you got H2, which is H and chronicle delta, right? The chronicle product. Sorry, couldn't draw very well. So this is chronicle product, H of H. That's going to give you H squared as something 1/2, 1, 1, 1, 1, 1 minus 1, 1 minus 1, and 1, 1 minus 1 minus 1. And we got 1 minus 1 minus 1, 1, right? This is my H squared. It's just the chronicle product. Okay? We just put here the same matrix, put in here, in here, in here, and the minus version here. So you got a 4 by 4. All right, H squared. So why did I do that? Because I know that 0, 1, you can actually express it in matrix terminology. This is 0, 0, which is 0. This is 0, 1, okay, which is 1, and then 0, and then 0, right? So all it takes to figure out the states in here, the combined state here, is just to multiply this with that. Okay, that's why I'm going to just write the state here, combined state 1/2, okay, 0, 0, minus 0, 1, plus 1, 0, and minus 1, 1. Okay? Why? Because of these two rows, right? The second row, 1 minus 1, 1 minus 1. 1 minus 1, 1 minus 1. And these are the basic states. Okay, that corresponds to each row or each column. Okay? Or you could do the following. You can actually figure out here to be 1 square root of 2, 0 plus 1, right? That's the superposition. And you know what this output is. This is 1 square root of 2, 0 minus 1, and then do the distribution. You get the same result. Okay? Because it's going to give you 0, 0, it's here, 0 minus 0, 1, it's here, plus 1, 0, it's here, and minus 1, 1, it's here. That's also another way. Anyway, you know now the input to this function, and you know the truth table of that function. Okay? Now you can actually compute the output here. If x, y goes in, for example, 0, 0, it goes in, I know what 0, 0 will come out if the input is 0, 0, right? So if this input is 0, 0, I know that it will come out with fi 0. Okay? So I'm going to actually now, this is after fi, what do I get? I get the following. 1/2, 0, chronicle product, fi 0 minus fi 0, so 1 cat. These are of course cats. It's a cat notation. Because every one of them is a cat, right? Okay, and I have got plus 1/2, 1 chronicle delta, again chronicle product, sorry. And we have fi 1 cat minus fi 1 XOR 1. Okay? That's what I got. So this is curly brackets. Okay, why? Because I've got these 0, 0s, right? So this 0, 0 creates fi 0, and 0, 1 creates 1 XOR fi 0. So that's why I have this 0 is as the x, right? That is the x. And I'm actually writing combined state. So that's why I've got 0 here. And this is fi 0 that corresponds to 0, 0. And 0 that corresponds to 0, 1 input. And plus 1, 0 input corresponds to 1 fi 1. See, 1 fi 1. And the other 1, 1 corresponds to minus 1 fi 1 XOR 1. Right? You get it, right? I just, put these, each one of the basis states through this circuit one by one, and then sum them up, because it's linear. Okay, it's just linear. Okay, here is one of the observations we have. For instance, for this particular example, I can actually rewrite this expression. How? The following way. Minus 1 raised to the power fi 0, okay, and cat 0 minus, this is a parenthesis, cat 0 minus cat 1. Why? Well, let's just think about it. If f0 is 0, right? If this is 0, because fi0 could be 0 or 1, right? So if fi0 is 0, then this would be 0 minus 0 XOR 1 gives you 1. So this is going to be cat 0 minus cat 1. Right? This is exactly here. And if fi0 is 0, that is minus 1 raised to the power 0 is just 1. That's going to give you cat 0 minus cat 1. So which is exactly this one. And the other possibility is that fi0 is 1. Right? If fi0 is 1, then this is going to be fi0 plus XOR 1 is going to give you 0. Right? Because 1 XOR 1 is 0. And this is 1. That's going to give you cat 1 minus cat 0. And if you look at this expression, if fi0 is 1, that's going to give you minus 1, right? Minus 1 raised to the power 1 gives you minus 1, cat 0 minus cat 1. But that is nothing but cat 1 minus cat 0, right? Same thing. But if you put a minus sign in front, that's going to flip it. Okay? So that's why I'm able to write this, because all these two options, two possibilities, can be covered by writing it this way. Okay, and you can similarly write this expression using the same trick. Minus 1 to the raised to the power fi1, and we have ket 0 minus ket. Okay, same idea. Because fi1 can be 0 or 1. Okay? Why did I write it this way? Because there's a common term, you see? Ket 0 and ket 1 in both of these. So that I can actually rewrite this expression in simpler term. So maybe actually write it here. Okay? So here is what I have. I have 1 over square root of 2 minus 1 raised to the power fi0 ket 0 plus minus 1 to the raised to the power fi1 ket 1. That's my first term. Second term is 1 over square root of 2 ket 0 minus ket 1. Okay? Why did I write that way? Because there's a 1/2 here. I divide this 1/2 to 2 1 over square root of 2's. 1 is here, 1 is here. Okay? Now, you see that this is 0 minus 1 fi0. Okay, this is here. And here 1 minus 1 fi1 is here. Okay, see? And the common term is what? Ket 0 minus ket 1 in both of them. See? That's why I actually put it out. Okay? Because they are the same term. Okay? So here's what you get. That's the final output. Why did I write 1 over square root 2, 1 over square root 2? Because this actually tells us something. This is a qubit state. You see? Square root of the 1 over the square it, you got 1/2. Square it, 1/2. Sum them, you got 1. So that's actually a valid qubit state. And that's also another valid qubit state. So these are not entangled actually. So these two qubits are not entangled. Why? We are able to write them separately. That's why they're not entangled. Okay? So this is a one state that corresponds to this one, and this is another state that corresponds to this qubit. Okay? So they're not entangled. Are we done yet? No, because we got an extra H, a Hadamard gate, before measurement. So let's just assume what happens to this Hadamard after the Hadamard gate for each one of these functions. See what the output would be if we select f0, f1, f2, and f3. There are 4 possibilities, and it's really not hard to go through each one of them one by one. Okay? And that's my final state. I'm going to go through them one by one and show you how the Deutsch algorithm is able to tell us whether the function is a balanced class or a constant class. Okay? So I'm going to go through them one by one. So first, if I equals 0, what happens? If I equals 0, let's just put it at 0 here. If I equals 0, f0 is 0 is 0, f0 is 1 is also 0. So that gives you, this is 1, this is 1. What I got is 1 over square root of 2, ket 0 plus ket 1, because these are 1. Okay? So I'm going to get 1 over square root of 2, ket 0 plus ket 1. That goes to a Hadamard gate, but I know what the output is after the Hadamard, right? Which is all 0, right? Ket 0, just the ket 0. It's just the reverse operation, right? You know that if ket 0 goes to Hadamard, you get that. And Hadamard is the reverse of itself. So when this superposition state goes to Hadamard, you get a 0. Okay, let's suppose I is 1. If I is 1, you see f1 0 is 0, f1 1 is 1. If you put it here, this is 0, this is 1. That means this is ket 0 minus ket 1. And 1 over square root 2 in front. So that is 1 square root 2, ket 0 minus, if I'm not mistaken, yes. That goes to a Hadamard. And the Hadamard output would be 1, right? Okay, if I is 2, then what do we get? If I is 2, f2 0 is 1, and f2 1 is 0. So this is 1, this is 0. That means this is going to be minus ket 0 plus ket 1. Okay? Minus ket 0 plus ket 1. Right? And you want another one. But you can actually put a minus sign here and then turn it into something like this. But this is identical to this. It's going to give you minus 1. Minus ket 1. Because of that minus sign in front. Okay? And finally, but we know that this is actually equal to this in physical space. Although the mathematical space are not the same, but we actually proven that putting a minus sign is not going to change anything from a physical perspective. That's why the cat1 actually equals to minus cat1, and when you measure them, you actually get 1 in both cases. And finally, equals 3, f0, f3, 0 is 1, f3, 1 is 1. You got 1 here, this is minus 0, plus minus cat1, minus cat0. I put minus sign in front, I got 1 square root 2 cat0 plus cat1. That goes to our Hadamard thing. But that gives me, again, same, minus cat0, which is equal to cat0 in physical rail. All right? These are all possibilities. And when you measure them, because that's latest stage here, you measure them. If you measure this, you get 0. If you measure this, you get 1. If you measure this, you get 1. If you measure this, you get 0. All right. I know that these two functions are balanced. Remember, and these two are constants. Right? It's balanced, it's constant. So therefore, if output of the measurement is 1, then you can actually determine that it's a balanced function, because both of these ones belong to the balanced. This is the output of the measurement that when the function is balanced function, the output of the measurement is 1. And when the function you choose is constant, then the output of the measurement is 0. You see 0, 0. So therefore, based on that measurement result, whether it's 0 or 1, you can determine the class of the function using Deutsch algorithm. And you only ask this question once, right? Because you use this function only once. Okay? This gate that is created based on the function selection. Somebody has selected that function. He doesn't tell you which function he selected. Okay? And then creates this gate and give it to you. Please go ahead and use it. And you use it only once. Based on the measurement result, you can actually say which class it belongs to. Okay? Whether balanced class or constant class. All right? Any questions?